All right, so the lab that we're going to do today is actually going to serve as an introduction to this concept of acceleration. So the second part of this trifecta. So the first thing was velocity. We figured that out. How do we represent motion? And then the second part is going to be acceleration of this unit. And the third part will be the culminating thing, which will be the next unit on forces, because force equals mass times acceleration. So you can't understand velocity, you can't understand acceleration unless you understand velocity. You can't do forces if you don't understand acceleration. You can't do acceleration if you don't understand velocity. So that's why it goes in the sequence that it does. So what you're going to do in the lab is fairly straightforward. You're going to take a ramp like this, and you're going to take a cart. We use these a lot, and you're just going to give this thing a push. That's going to go up, and then oddly enough, it's going to come back down. So what that allows us to do is study that motion, but it's like it's like a slowed down version of gravity. So there's a couple of things about these parameters. First off, you want to make sure that when you set this up, if you look on this actually has like a meter stick kind of taped to the side of it. Make the 0 on the bottom side. So we're going to make 0 the reference point, okay, so that everybody's the same. So like here's going to be the reference point. And this is actually marked off in centimeters, but make sure you convert that into meters, divide by 100. It goes up to 122 centimeters. So you're going to give this cart a push, okay? All right? Now, listen to me. Don't include the push, okay? You're going to start this analysis from the second that it leaves your hand until the point that it comes back to that point, okay? So don't include the push. You're going to start looking at this situation as soon as it leaves your hand and then when it gets back to that point, okay? So what that means is that your velocity time graph is not going to start at 0. Okay, your velocity time graph is going to start with some big positive velocity. Now, obviously, when you do this, put the wheel sides down, because if you try and do it like that, it's not as cool. It's like, okay, well, that was exciting. Right, cool. No, okay? So we do this to minimize the amount of friction. So when you give this a push, boom, there you go. Now, in terms of the data that you need to collect, you need to make a decision as a group. Are you going to measure everything from the back of the cart or from the front of the cart? I don't care, okay? But it's going to be important. So if Peyton's going to give it a push, okay, then, and Adana's going to be timing it, you need to mark it either where the front of the cart is when Peyton lets go of it, or the back of the cart. I don't care, okay, but just pick one. So then, if you're going to go off the front, okay, then you need to know where the front of the cart is when it leaves Peyton's hand. But then you need to mark the front of the cart up here. And then stop it when the front of the cart gets to that point. Because if you don't do that, then you're going to be off by like the length of the cart. So I don't want Tyler marking where the back of the cart is here, and then Derek marking where the front of the cart is up here. There's no right or wrong answer. You just have to make sure everybody's going off the same point. So here's what you're going to do. So let's say, for example, I'm going to mark this, and let's say my initial position is 10 centimeters. Okay, that's where it was when we started the analysis. And it rolls up here, and let's say the front of the cart ends up here at 110 centimeters. Okay, those are my 2 points. So then it's going to return back to 10 centimeters. So we can oddly enough draw a position time graph. So I'm going to give you 3 options on the position time graph. Okay, so here's 10, there's 110. So you can have a graph like this. So there's curve A. You could have B, and then you could have C. Okay, so those are your there's your three potential position time graphs. Curve A, which is this nice parabolic curve. Curve B, which looks like a triangle. And C looks like an inversion of A. Okay, so those are your three options. So how many vote A? 1, 2, 3, 4, 5 is kind of gaining momentum. 6. What about the middle line of B? Nobody's on the B train. What about C? Some of you did not vote. This is America. People died so you had the right to vote. For the love of Lord.
What did you just say?
I said,
I was thinking you draw the graph and then I didn't hear the question.
which position time graph represents that motion? A, B, or C? So there was A, which is the parabolic curve, B, which is the straight sloping lines, C, which goes up like this and then comes back down like that. So that's what we're trying to figure out, is what's the position time graph going to look like. So, for those of you that voted A, who wants to be the spokesperson and tell me why you voted for A? Nathan?
I voted for A because you can see as the line goes up like that, the velocity slows down as it peaks and then it speeds back up as it goes back down.
Fantastic, okay? And this harkens back to this whole idea. Oh, what does the slope of a position time graph gives you? Oh, it gives you velocity. So if you look at this motion, okay, when is it going fastest? What are the 2 points it has its biggest speed? Beginning at the end, right? So now, does the cart change direction? So what does your velocity have to do? Change sign. It's going to change direction. What are the 3 things that it has to do to change the direction? Slow down, hit 0, speed back up. Does it do all 3 of those things? Yeah. Slow down. This is the quintessential poster child of something changing direction. Slows down, stops, speeds back up. Velocity changes sign. Okay, that's cool. All right. So, what if you chose B? It's not right, but what would B look like? If I said, okay, we think B is the motion, what would B look like?
Consistent.
Well, you have a straight sloping line, which indicates what? Constant velocity. So if B was right, I would push it and would move up at a constant velocity, and then it would come back down at a constant velocity. Didn't see that? Can't be B. All right, so B is out. All right, no B. Now, C would be coolest, okay? Because if C was right, you'd push it, and it would start off really fast. It would start off slow, because it's a shallow curve. And then it would speed up on the way up, then it would come back down, and it would slow down right before it got back down to here. So you'd start slow, fast, then slow down as it got to here, which would be cool to watch, okay? But you're not going to do that without rocket engines and brakes and things like that. So that leaves us with curve A. Now, here's the deal. When you draw your graph, you're just going to kind of have to draw a general idea of what it's going to be, okay? You're not going to know the exact positions of this thing throughout the entire trip, but you're going to know the general shape of it. Now, let's talk about time. With this one, unlike the cart where it would roll and it hit the wall and then it bounced back, and we had some people time it like in each interval, that's not what we want to do on this one. You do want to have 2 people timing, but just so you can compare the times. So you want to time it the entire trip from when it lets go to when it gets back to that point. Okay? So don't have somebody time it on the way up and another person time it on the way down. Okay? We just want to time the entire trip. but you want to have two people timing to make sure that you have good data, okay? Now, if you're off by like a half a second, like one person gets 1 second and the other person gets 1.5 seconds, we'll just take the average. No, if you are off by a half a second on that small a time, that's a big gap. Somebody screwed something up. Your time should probably be within a couple of tenths of a second. You can take the average, but just make sure that they're relatively close. So let's say we time this, and the entire time, start to finish, was 2.20 seconds. So that's from the time that it leaves your hand until the time it gets back to that point. And again, don't include the push, okay? Start that stopwatch as soon as it leaves Peyton's hands. Boom, boom, back to that point, okay? Don't include the push. So if it took 2.20 seconds, how long do you think it's going to take to reach that maximum distance from the starting position? Total time was 2.2. How long do you think it took to go up? Don't make this difficult.
1.10 seconds.
Yeah, perfect. So what we're going to do is we're going to assume that this is symmetrical, okay? And you can do that as long as it returns back to that same point. So what we're going to assume is that this point up here was 1.10 seconds. So at half the time is when the velocity is going to go to 0, and then it's going to start speeding back up. And this is here's the cool thing about this position time graph, okay? And it goes back to what Mr. Fisher said. At time 0, this is when you have your biggest positive velocity. That's cool, right? And then as time goes by, your tangent lines are becoming more and more shallow because it's slowing down. At 1.10 seconds, if you draw that tangent line, that has a slope of 0, because that's when it's going to change direction. And then it's going to come back down. The tangent lines are going to go negative, and they're going to become steeper. Right. So this shows the 3 criteria for changing direction. You're slowing down, you're stopping, and you're speeding back up. It's cool. Okay, now, let's talk the velocity time graph. So on your velocity time graph, I'm going to give you some options on your velocity time graph. Okay? Yeah, that wasn't good. Oh, come on. Go. So this is like 2 sets of lips. So here are your options on what your velocity time graph is going to look like. Option A, it says it's going to kind of start shallow, get faster, steeper, and then shallow out again. Okay, so that's option A. Option B is just a straight line connecting the 2 points, kind of boring. And then you have C, which starts shallow, or starts steep, becomes shallow, and then gets steeper again. So those are your 3 options for a velocity time graph. It's going to be one of those 3, A, B, or C. So how many vote is going to be A? Okay. What about B? 1, 2, 3. Okay. What about C? Kind of an even split between B and C, but nobody's on the A train. Okay? It's interesting. So, how can we settle this? Let's start with this idea. What does the slope of a velocity time graph give you? Slope gives acceleration, right? True? Slope equals acceleration. That's key number 1. Slope equals acceleration. Do you all agree that the cart accelerates throughout the entire time? Is everybody cool with the idea that it's accelerating? Okay. It's accelerating because the velocity is always changing, right? Now, this goes back to this whole idea, we'll talk more about forces later, this whole idea of Jedi-Stoffel law. Stop the force and watch what happens. So I want you to visualize this. And this would be the ultimate thing to have in the physics classroom. And that's like a gravity switch that I could turn off, okay? So imagine that I could give this a push. And as soon as it leaves my hand, I shut off gravity in this room, okay? I give it a push and I shut off gravity. The second it leaves my hand, I shut off gravity. What would the cart do?
Keep going.
Yeah, it would just go like this, right? And it would go and it would go and it would go, and then it would do like this, which would be exceptionally cool to watch, okay? So, if you stop the force and watch what happens, this is this Jedi-Stoffel law. Stop the force and watch what happens. But if you look at this from the perspective that Mother Nature is a lazy prima donna, Mother Nature was all about the lowest possible energy state. So why do you think the cart returns back to this point? Is it at a higher energy state when it gets back here, or is this the lowest possible energy state? Highest or lowest?
Lowest.
Lowest. Mother Nature wants to be at the lowest possible energy state. That's when she's most stable. She's a tie-dye, gray-haired, hookah-smoking, Birkenstock wearing old lady that just wants to chill out. Okay? If this was the most stable arrangement, that's where it would stay. And it would stop right there, which would be kind of weird. It's like you push it up there and it just stops. Huh, weird. Okay, that's different. Okay? But it comes back down because that's the lowest possible energy state. So the reason that it accelerates goes back to this sign back there. It says F equals ma. So if I get something in motion and there's no force acting on it, it will maintain that state of motion. So if I stop applying a force and I watch what happens and I see it slow down and then speed back up, the only way that's going to happen is if there's some external force acting on it. Because for lack of a force, this thing would just keep going and going and going and going and going. And so because I see it change direction and I see it speed up and I see it slow down, that means there has to be a force acting on it. Because Mother Nature isn't going to do this on her own, because Mother Nature is lazy prima donna. So Mother Nature is going, I don't care, if you give that a push and there's no force, it's just going to keep going. So by virtue of the fact that I see it speed up and slow back down, that tells me that there has to be a force acting on it. Okay? Now, the big red sign in the back that says F equals ma, right? As it goes, does the mass of the cart change? No, we don't drop an elephant on it halfway through, okay? We don't lose part of the mass. Mass stays the same. So mass stays the same. Mass isn't changing. Now, F equals ma. We know there's an acceleration, right? We know that there's an acceleration because it slows down, stops, and it speeds back up. So there's an acceleration. So that means there has to be a force. Okay, by logic, if the mass doesn't change and there's an acceleration, that means there has to be a force. Okay? Now this is kind of poetic, but not really. What's the source of the force that makes it accelerate? Let me give you a hint. Rhymes with gravity. Gravity. Oh, right, gravity. Cool, right? Kind of important that we have that. Okay, we wouldn't be here having this discussion without gravity in the universe. So, gravity is going to make it slow down, and then gravity is going to make it speed back up. Do you think gravity is going to provide the same amount of force throughout the entire time? So let's think this through. If the force is the same because of gravity the entire time, and the mass is the same, because we're not going to change that. So if the force is the same and the mass is the same, what has to happen to the acceleration? It has to stay the same. Oh, right. So which of those three graphs shows the same acceleration the entire time? A, B, or C? B. B is the one that's right. Now, for those of you that chose A and C, it's not your fault. It's Nike's fault. It's the Nike swoosh. You all associate, ooh, it's speeding up and it's slowing down, we have to have curved lines, okay? Ooh, it's exciting, right? It's not the Nike stick. It's the Nike swoosh, right? But here's what you have to remember. Acceleration is not how fast you're going. Acceleration is the rate at which your velocity changes, okay? That's the whole point of acceleration. It's the rate at which your velocity changes. So even if you look at this cup, and I chose this cup just for today, okay? So it's not the velocity final equals velocity initial plus AT, which we'll use this equation today, okay? That kills you. It's the F equals M change in velocity over time, okay? So change in velocity over time is your acceleration, okay? So this is just saying nothing more than F equals MA. So it isn't your change in velocity, it's the rate at which your velocity changes. That's what's reflective of the force. So what we're going to say is that our rate of change in our velocity per unit of time is going to stay the same. That's the acceleration. Mass of the car is going to stay the same, therefore we have to have the same force. So don't confuse an object going fast or going slow with acceleration. Okay? It's the most common misconception. So your velocity time graph is going to be pretty boring. Okay? You're just going to pick a point of some positive velocity and you're going to draw a line down like this. It's the only time I'm going to ask you to draw a graph without knowing the data. Perkin, man, we can't do this. It's like, oh, we'll get this. We'll get this. So, if you look at this data of 2.20 seconds, okay, here's the question. The total time was 2.20 seconds. All I know is that I'm going to start with some positive velocity. Okay, that's all I know. I'm going to start with some positive velocity. Total time was 2.20 seconds. How long is it going to take for it to reach that point, and where is it at that point?
1.1.
Huh?
1.10 seconds.
Why?
Because it's half the distance. That's when it's up at the top of the ramp.
Okay, and what's this is the velocity time graph, right? So at 1.10 seconds, what's the velocity? Zero, because that's when our tangent line has a slope of 0. So at half your time, that's when your velocity goes to 0. Okay? That's it. That's when your velocity goes to 0. Now, you're going to start over here with some positive velocity that you're not going to know. You're just going to pick a point. You're just going to draw a line. Okay? But we can find that. Oh, WordCamp, how can we do that? Well, here's what we cannot do. Okay, here's what you're forbidden from doing in this lab and on the entire acceleration unit. What we cannot do is take distance, how far it goes, and divide that by time to get a velocity. Okay, I'm gonna lay this groundwork right now. This is a beautiful equation, but it only works, and listen to me very carefully, my children. It only works under one specific circumstance, and that's if you have constant velocity. And if you have constant velocity, you're not accelerating. Guess what this unit is called? What are we going to study? Acceleration. Okay? So in this unit, if you ever find yourself trying to take distance and divide it by time to get velocity, or go, oh, time is distance divided by velocity, stop. Don't. It's wrong. I promise you. Okay? So if you're addicted to this equation, WordCamp, I love distance equals velocity times time. Love that. It's in my... Stop. Okay? No. Don't. Don't. Get help. Okay? Stop. In this entire unit, I promise you, You are not going to take distance and divide it by time to get a velocity, because that only works under constant velocity. Don't do it. Don't. And you sit there and go, oh, Mr. McKemp, we won't do that. It's like, you lie. Okay. But we're clever, right? We're clever. We're going to find this velocity, but we can't do that. What does the area underneath the velocity time graph give you? Displacement. Oh, area of a triangle, correct me if I'm wrong, is 1/2 base times height, right? True? Okay. If you're the member of the area of the triangle club here at the high school, you know that, right? That's what you have on the back of your letter jacket. Area equals 1/2 base times height. Devin, are you a member of the triangle club?
I wish.
Okay. Maybe we ought to start that.
Yeah.
It's a triangle club. Okay. All right. So anyway, so here's our graph, right? So in this situation, we're going to know 1.10 seconds. We're going to know how long it's going to take to get to 0. It's kind of cool, right? So we're going to know the base of the triangle, which is going to be half of our time. Now, we just said area represents what? We're going to know where it starts. I want to know where it's going to end up. We can do displacement. Because remember, displacement is also position final minus position initial. So on the way up, we're going to look at this in two different situations. On the way up, we're going to know the initial position. Maybe it's 10 centimeters or 0.1 meters. And we're going to know the final position, which is going to be like 1.10 meters. So we're going to know the initial position on the way up, and we're going to know the final position on the way up. So, right, we're camp displacement is position final minus position initial. That's cool. So, if I take 1.10 meters minus 0.10 meters, oddly enough, I get the displacement of 1 meter. So I'm going to know my area. That's cool. So now I'm going to know the area of the triangle because I know my displacement, because that's what that represents. I want to know the base because I'm going to know how much time it took to happen. So what does the h represent? The height, which is going to, what is that going to represent on the velocity time graph? Yeah, my initial velocity. So when I find this height, that's going to represent my V naught. I'm going to know how fast this thing was going at the beginning. Okay? So we're not going to measure the velocity, but we're going to find it. Because we know area equals 1/2 base times height. So if I go to this, area equals 1/2 base times height, and I solve this for height, I get 2a divided by b. Now, one of the things you want, I'm going to begin to stress to you again and again and again and again and again and again and again, is that you solve the equation first, and then you put in the numbers, okay? You guys are not squirrely little freshmen in an Algebra 1 class. I've heard she had 8th graders, okay? Okay? You're running with the big dogs. How science is done at this level is that you solve the equation first, and then you put in the numbers. And it's also going to allow you to see like more of a deeper relationship as well. So in this situation, I'm going to solve this. So I'm going to take 2 times my area, which would be 1 meter, and then I'm going to divide that by my base, which is 1.10 seconds. Now, look what happens with the units. Oh, I get meters divided by seconds. Oh, that's a velocity. That's cool, okay? Because if this didn't work out to be meters per second, guess what? I'm dead in the water. Now, I can't use the equation. It looks cool, but if the units don't work out to be meters per second, I'm dead in the water. So what this is going to allow me to do, so that's 2 divided by 1. So somebody take a calculator, take 2 and divide it by 1.1. You should get like 0.9 something. Just take 2 divided by 1.1. What'd you get?
1.82.
1.82? Oh, that's right, 1.82. I was way off on that one. Wow, that sucked. Okay, I was thinking 1 divided by 1. Yeah, about 1.82 meters per second. Okay. Now, here's the next big equation that you're going to look at. And that's acceleration is v minus v naught over time. Okay? So, in this situation, on the way up, when it gets to this point, what's my final velocity going to be? 0. My initial velocity, we just said, was 1.82 meters per second. So I'm going to take 0 minus 1.82 meters per second, and I'm going to divide that by 1.10 seconds. Now, look what happens with the units. I'm going to take meters per second, I'm going to divide that by seconds. Do I get meters, because the seconds cancel out, or do I get meters per second squared?
Meters per second squared.
I better get meters per second squared, because that's what acceleration is measured in. And if you don't believe me, take meters per second times 1 over seconds, which is the reciprocal. Oddly enough, you get meters per second squared. So this is a rate function. It tells you the rate at which your velocity is changing per unit of time. So this slope, when I get this number, so somebody take 1.82 and divide that by 1.1. .65 meters per second squared. Okay, so there's my acceleration. So what that means is that for every second that goes by, this is the rate at which my velocity changes. Okay, so if I started at 1.65 meters per second, 1 second later I would be at 0. Another second later I'd be at negative 1.65. Now, conveniently, notice that this slope works out to be a negative value. Oh, that's cool. Look at my velocity time graph. My velocity time graph has a negative slope. Oh, that's cool. Slope represents acceleration. Now, at this point, everybody's cool with what we have going on. Oh, right, Bergkamp. It's slowing down. We have negative acceleration. It's cool. Things slow down with negative acceleration. This isn't why I wrote the lab. I did not write this lab for on the way up. I wrote this lab on what's going to happen on the way down. Now, on the way down, what's the initial velocity going to be? 0. So what we're going to do is we're going to look at this like in 2 different flights. On the way up, we start with some positive velocity, and that's going to go to 0. On the way down, we start with 0 velocity, and then we're going to end up with a negative velocity because we change sign. So on the way up, everybody's cool. Positive velocity, negative acceleration. I'm slowing down. Everybody's hip with that because they have opposite signs. The reason that I'm going to have you do this lab is to force you to realize that you can speed up with negative acceleration as well. So on the way down, everybody wants to make acceleration positive. Oh, you're speeding up. Bergkamp, we should have positive acceleration because it's speeding up, because you all want to associate positive acceleration with speeding up, not negative acceleration. But here's the whole point, is that if you look at your velocity time graph, okay, right here, notice that that slope is the same the entire time, okay? It's the same slope. If you want to say, oh, I have positive acceleration on the way down, then your graph would have to look like a V, okay? So what would have to happen? Now, this harkens back to F equals ma. As soon as you let go of it, what's the only force acting on the cart? Gravity. Okay, it's a pretty constant force. So this is going to be a bigger truth later on. If you want to change the slope of a velocity time graph, either numerically change it from -5 to -6, change the sign, positive or negative, the only way that you can change the slope of a velocity time graph is to change the acceleration. And the only way you can change the acceleration is to change the force. Okay? So when you let go of it, because it's the same force acting the entire time, that's why I get the same acceleration the entire time. Now, one of the things you're going to have to draw is what we call a motion diagram. And I'm going to tell you how I want this to play out. So over here on page 3, okay?
TV keeps glitching out. Like when you draw, it glitches and
Okay, well that's weird. I'll draw slow. Okay, so, all right, so here on page 3, you've got this graph that looks like this. That's so weird. Okay, so what you want to do on these motion diagrams is that you want to show how the velocities are changing and how that's reflected in acceleration vectors. So what you're going to do is you're going to come in here and you're just going to draw a V1, okay? That's the initial velocity that you're going to give the cart, okay? Just draw an arrow, V1. Now, one of two things is going to happen as that cart goes up the hill. Come on, show me my V1. Show it to me! There we go, there's V1. So, one of 3 things actually is going to happen as the cart goes up the hill. Option number 1, as it goes up the hill, the velocity vector just stays the same. It's going to stay the exact same length and it's going to point in the exact same direction, which indicates that this thing has constant velocity going up the hill. That's option number 1. Option 2, the velocity vectors are going to get smaller because it's going to slow down. Option 3, the velocity vectors are going to get bigger because it's speeding up. Okay? Those are your options. Same, smaller, bigger. What do you think is going to happen on the way up? Smaller, bigger, stay the same? Smaller. They're still going to be pointing up, but they're just going to be smaller. So you come in here and go, okay, here's V2. Okay? So my second velocity vector is a little bit smaller because it's slowing down. And then you could come in here and go, okay, here's V3, even smaller. So as soon as you see velocity vectors changing, that means you're accelerating. Now, get out of your minds right now. The other reason I wrote this lab. Get out of your minds right now the thought that acceleration only means that you speed up. Acceleration is just a change in velocity. So when this thing is going up the hill and it's slowing down, it's accelerating. But that acceleration is making it slow down. Now, on the way down, what are those velocity vectors going to do?
get bigger.
They're going to get bigger. And which direction are they going to point? Down. There you go. Now, here's the deal. As soon as you see velocity vectors changing, you're accelerating. So your acceleration vectors can only do one of 2 things for now. For now. Either your acceleration vectors point in the same direction as your velocity vectors, or your acceleration vectors point in the opposite direction. So if you're going to slow down, do you think your acceleration vectors are in the opposite direction of your velocity vectors, or do you think they're in the same direction?
Opposite.
Opposite. Because if things slow down, what do you know about velocity and acceleration? It's a direction. So what this means is that on the way up, I'm going to have some negative acceleration. Now, there's 3 ways in this lab I'm going to make you look at acceleration. Count them 3. Okay? 3. One is the slope of your velocity time graph. Oh, it's a straight sloping line. That's option number 1. You can also calculate it using A equals V minus V naught over time. That's the second way that you're going to look at acceleration. And the third way is going to be when you draw your acceleration vectors, okay? So when you draw your acceleration vectors, as the cart goes up the hill, your acceleration vectors can also do one of three things. Your acceleration vectors can get bigger, your acceleration vectors can get smaller, or your acceleration vectors stay the same. So when you draw on question number 23, when you draw those three acceleration vectors, you need to decide, are they the same length? Are they getting bigger or are they getting smaller? If you want me to think that they're getting bigger, you draw those acceleration vectors getting bigger. Okay, I'm not going to take a ruler and guess and go, well, I don't know, it's a couple of centimeters, a tenth of a centimeter difference. Gee, I don't know. No, okay? If you want me to think those acceleration vectors are changing in magnitude, you clearly draw them so that they are changing. If you think those acceleration vectors are staying the same, you draw them the exact same length. Okay? That's a decision that you have to make. Okay, so here's what's going to happen. So now that we have all this background information, let me get you through that. Now, down here on procedure, some of you need to read this and pay attention to it. I say, in big bold letters and underlined, I said include all numeric values in every calculation. If you calculate displacement, if you calculate area, if you calculate acceleration, okay, I want to see those calculations in every one of them, okay? The purpose of a lab is to convey information, not to write down numbers, okay? It's to convey information. So like, you're going to record the angle. If nobody's phone has a good app that measures angles, let me know. I'll bring my phone over and we're going to need the angle of the incline. So if you don't feel good about, if nobody has a good angle app, I've got one, let me know and we'll record that angle. You're going to need total time, okay? At least have two people time this thing. They should be pretty close together. Take the average of the two. The initial position of the cart. We're making the bottom of the cart the reference point. We're making that point 0. So you're going to judge all positions from that reference point at the bottom. And again, I don't care. Decide if you're deciding you're going to go off the back or you're going to go off the front. I don't care. Pick one. Okay? Just decide so that everybody's consistent. So on the way up, you're going to have the initial position of the cart. Make sure that these are in meters. These are marked off in centimeters. Divide by 100. I have all the faith in the world that you are capable of doing that, dividing by 100. Then the final position of the cart, then you're going to calculate displacement. You're going to use position final minus position initial. Guess what? I want to see that calculation. Then you're going to have half the time. Now, on the way down, you're going to start here, and you're going to end up down here. So on the way down, the initial position is going to be this point up here. And again, make sure you're going off the front or the back. Don't care, pick one. And then your final position is going to be down here, and then you're going to have that displacement calculation. Do you think your displacement is going to switch signs from positive to negative? Mm-hmm. Yeah, it will. Okay, so you should have one positive displacement, you should have one negative displacement. Then you have a bunch of questions to answer. Now, when you get to question 5, okay, and I give you this equation that A equals V minus V naught, there's a couple of ways you can do acceleration. When you answer question number 5, you don't know what the initial velocity is going to be. You haven't found it yet, but you know it's going to be a positive value. So there's a couple of ways that you can calculate or explain this. One is that you can use A equals V minus V naught over time. Realize, oh, my final velocity is going to be 0. My initial velocity is going to be some value. I can look at the sign of my acceleration. You can look at it in terms of, hey, it's speeding up or it's slowing down. Okay? I don't care. Okay? Pick one. Then you're going to talk about what's going to happen on the way down. Okay? Now, notice on question number 6 in big bold letters, I typed out the word speed. Remember, speed is just how fast you are going. that isn't positive or negative. Speed is just, hey, I drove 50 miles an hour. Well, that was cool, except for that was a speed school zone and you just got a ticket. But if you just tell me I drove 50, that's just your speed. Now, if you said, hey, I drove 50 miles per hour north, then it becomes a vector quantity. So one of the most important things, and this is only true if it's symmetrical, we're going to assume that the speed that it has when it leaves is the speed when it gets back down. And we're going to do the same thing if you throw an object up in the air. If you throw something up in the air and it comes back to that same point, we're going to assume that the two speeds are the same. Now, if I throw it and then it falls all the way down to the ground, oh, it's going to make noise. Okay? Then it's not the same. But as long as it returns back to that same point, the same speeds are going to happen. Okay. So, on number 7, I'm going to give you all one sheet of graph paper. You're going to split the sheet of graph paper in half. You're going to sketch a position time graph at the top. You're going to draw a velocity time graph at the bottom. This is just a sketch. You don't know the exact positions at every point on the graph, but you know what that's going to look like. You're going to know what your maximum height is going to be. You're going to know how much time it's going to take. Okay? So you can at least make a symmetrical sketch about what's going to happen. Then, when you get over here on page 2, then I said, why didn't the slope remain constant? There should be 2 parts to your answer, okay? Look at what's happening on the way up, look at what's happening on the way down. You want to talk about magnitude, you want to talk about direction. When you get to number 9, this is when you're going to draw that velocity time graph. So here's going to be your sheet of paper. Your position time graph is going to look something like this. Your velocity time graph is going to look something like that. Okay? You don't know all the data, but we're going to figure that out. When you get to 15, this is when you're going to talk about just your velocity time graph. What does the area represent? Is it distance? Is it displacement? Is it acceleration? What is it? Then on number 16, you're going to use this area for a triangle. This is what we just talked about. You're going to have 1/2 base times height. Solve the equation first, and then put in the numbers. Now, this is what will drive me absolutely insane. Let's say you do number 16, and this is what I see. 2 times 1.1 divided by 0.7 equals something, and not a single formula, not a single unit, nothing. This means nothing to me. I have no idea what that means, okay? I don't know if you're calculating velocity, acceleration, penguins. I don't know what you got, okay? Make sure you put units. Then, you're going to calculate acceleration. So when you get to number 17, you're going to use the idea on acceleration. That is v minus v naught over time. Okay? What's your final velocity on the way up? At that point, you're going to know the initial velocity, find your acceleration. If you are a math nerd, all I'm asking you to do is find the slope of that velocity time graph. Okay? Wow. I didn't realize this was such a large time lag. That's annoying. I love technology. Okay, so if you're a math nerd, find the slope of the line. Pick 2 points, find the slope of the line. Now, when you get to question number 21, this is when you're going to need your angle, okay? So on 21, and make sure that you're in degree mode, and later on, when we get into forces, you'll see where this equation comes from. For now, just accept it, but later on, you'll see it. So A equals negative 9.8 meters per second squared times the sine of the angle. So this is the one time you're going to use the sine of your angle. So you're going to take negative 9.8 times the sine of like 3 degrees, 4 degrees, whatever that is. What that's going to give you is a theoretical acceleration. Okay, that's assuming that there is no friction. That's a theoretical acceleration. Now, when you get to, on the back side, when you get to question number 22, you want to calculate the experimental error. The formula for experimental error is on your equation sheet, okay? So experimental error is theoretical minus experimental divided by theoretical times 100. It's an absolute value, okay? It's an absolute value, which really doesn't make any, means it doesn't make any difference which way you subtract, because it's an absolute value anyway. So basically, what you're going to do is you're going to take your answer to number 21, which is your theoretical value. You're going to use that answer to 21 down here as well, and then you're going to have your answer to number 16. So basically, love this. I was like, God, I wish I just had like chalk. So you take your answer from number 21, subtract your answer from number 16, so divide by your answer to number 21, take the absolute value of that, multiply by 100. Now, what you have to be careful of are these are all negative values. So it's like a negative minus a negative divided by a negative, so pay attention to that. When you get to 23, this is where you're going to draw your velocity. 3 velocity vectors, 3 acceleration vectors on the way up, 3 velocity vectors, 3 acceleration vectors on the way down. On 25, you're going to use the same idea on 25, but imagine this. You're going to take a ball and you're going to throw it up in the air, and you're going to see how long it takes for that ball to be up in the air. So it's going to go to a height of 5 meters. Give you some reference, this ceiling is about 2.5 meters, okay? So 5 meters would be about twice as high as the ceiling. So imagine this, I'm going to throw this thing straight up, I'm going to time it, it's going to land exactly 2 seconds later, it's going to go up to a height of 5 meters. You're going to draw a position time graph, velocity time graph, and do a bunch of those calculations. All right, I'm done. You're on your own. So, here we go.